So this is work with Roy Livni and Shai Shalev Schwartz. Right. So we're looking at the semi-supervised learning. So many learning problems, the case is that you have a lot of unlabeled data, practically unbounded, and some labeled data. And the issue is, or the question is, what can you do with unlabeled data, in the sense that if you know the distribution of unlabeled data, and here we're actually going to assume that you know the exact distribution of unlabeled data, although we can change that as well. How does that help you use the labeled data? Can you use much less labeled data in that case? So of particular interest to us, and actually there's something that's been used a lot for semi-supervised learning, is what's called the manifold assumption. So input points in your input points X don't typically occupy all of space, but some structure in space, say a manifold. And so it's reasonable to assume they lie on some structured manifold. And the question is, let's say you know the manifold that the data resides on, can that help you learn from unlabeled data? Okay? So let's say you just know the points, the structure of in space that the unlabeled points reside on. Can you use that to better use labeled data? So what we show here is that you can use this structure, in the sense that there is a provable gap between supervised learning and semi-supervised learning in this setting of where you know something about the data manifold, and without making any compatibility assumption. So what are compatibility assumptions? So this is one of the nice cases where you can show that semi-supervised learning does help beyond supervised learning. So this is a framework by Balkanen and Blum and others to explain the efficiency of semi-supervised learning. So the idea is that in the case where the distribution over the features, so this is d of x, so this distribution over x space, so in the case where d of x and the classifier y f of x are compatible in some sense, then you can show that semi-supervised learning will have better sample complexity than supervised learning. So what do I mean by that? So for example, if you know that your separator, namely f of x, passes through a low density region in your X distribution, then we call that, or it's been called by Balkan and Blum and others, compatibility between data distribution and the classifier. And in this case, you can show that there is a gap between what you can do with supervised learning and semi-supervised learning. Another example more relevant for us is that, for example, if you know that the separator is continuous on the manifold, so the separator, the function f of x is continuous on this manifold, namely that closed points have similar f of x values, then again you say that these are compatible, that the data distribution is compatible with the classifier, and therefore you can learn with less data if you know the data distribution. Okay, so these are two examples of compatibility. Namely, they assume that the data distribution conveys some information about the classifier. Okay, so these two are correlated. And in this case, you can show that there's a sample complexity gap, which depends on how compatible things are. Okay, and what we wanted to ask was whether you can show this gap without any compatibility assumptions, and specifically for the manifold case. So it's not at all clear that there is a gap actually when you don't assume compatibility, and it's actually been conjectured by Shai Ben David at the time that you cannot, that SSL is not better than supervised learning when there is no compatibility. Okay, but actually it was shown in 2013 by Darmstadt and colleagues that semi-supervised learning does help, or can help, even without compatibility. Okay. So they showed a nice example for discrete inputs whereby there was no compatibility, but there was still a sample complexity gap between supervised and semi-supervised. Right. So what we want to show is a similar result to Darmstadt, but in the case of continuous features, and where what you have is a manifold structure for the input features. Okay, so that's what we've shown. So some quick definitions. So given a supervised learning algorithm, namely one that doesn't use the unlabeled distribution, we denote by M its sample complexity. and the semi-supervised algorithm B that takes the data distribution as input, we denote its sample complexity by M of B. And we say that SSL benefits from unlabeled data if for any constant C, there is a gap of C between these two sample complexities. So the unlabeled sample complexity is arbitrarily better than the sample complexity, the supervised complexity. Okay. So here's the setup for which we can show this. Yes? No, for every constant there exists a distribution that demonstrates the gap. Okay. Okay. So here's the setup that we consider. So the hypothesis class that we consider are algebraic sets. So sets that are classifiers that are one on a manifold, on an algebraic manifold, namely the set of x's for which a certain polynomial vanishes. So here are some examples. And the distributions that we considered, this type of distributions over the feature space are unions of k irreducible algebraic sets. So things like a union of circles or two functions where we call something irreducible if you can't break it down into two separate algebraic sets. Okay? So this could be like a union of spheres or union of cylinders, etc. Okay, so these unlabeled distributions are sets of k irreducible algebraic sets. Okay? So that corresponds to the manifold assumption. So here's the algorithm. It's pretty simple. You have the unlabeled data distribution. You break it down into irreducible components. Now, the true hypothesis is an algebraic set by our definition. So therefore, this algebraic set has to be one of the two. Either it's equal to a union of components, of these components, or it has a null overlap. So for example, if your true hypothesis is this hyperplane, then its overlap with either of the components has a measure 0. And in that case, nothing matters, right? So basically, the idea is that either you know what the components are, okay, and you have to fit one of those, or it doesn't matter, okay? So the algorithm is simple, and it's simple to show that this is its sample complexity, the semi-supervised learning algorithm. Okay, so it's k over epsilon log 2 over delta. So that's the sample complexity for the semi-supervised algorithm, namely the algorithm that knows the unlabeled data distribution. And most of the work is actually to show that the supervised algorithm that doesn't know d of x is bound to fail. Okay, so this is where most of the technical work is. And the key ideas are, so for the data distribution, what we use to show this gap is just a distribution with two components in R2. And these components are reflections of the of each other. Okay, so this is so you see this is minus that. So we use a union of two functions, one which is the minus of the other. Okay, so that's what we use to demonstrate the gap. So there are many technical challenges in showing this. Basically, you need to show that there's a generative process using a probabilistic argument. This generative process is where you sample things like this and then test them on a new example, that you'll get arbitrarily bad generalization error. And it's tricky to show this, and to do this we use this thing called the co-area formula, which helps you do integration over level sets, and that helps us treat this generative process of data distributions and labeled data. So the key thing to notice is that there's this mapping between labeled samples and unlabeled distributions, which we use, and then we use the inverse map with the co-area formula to get what we need. Okay. All right. So there's the way of doing this practically using subspace clustering, so we can actually implement this algorithm efficiently. Right. So basically, the conclusion is that SSL improves over SL for manifold structure. The analysis is pretty tricky, and it's practical. And open questions are what other geometric-based settings have the same property. So, thank you. Yes. Right.
Yes, do you have any upcounts of the number of unlabeled examples that you need in order to make it
Right, so we assume that the unlabeled data distribution is known exactly.
I know, because that's an assumption of infinite.
Right, yes.
Can you show that finite remaining suffice to have a boundary?
So there are results for subspace clustering that for recovery in subspace clustering. I mean, how many examples do you need to recover the subspaces in a union of subspace? So we can use something like that to get, but we didn't do it in the paper.